So here we are for section 3.5 in chapter 3, and this time we're going to be looking at some special cases. So far we've looked at what happens when we have real eigenvalues, what happens when we have complex eigenvalues with imaginary parts, but we've kind of skipped over one of the important possibilities when the characteristic polynomial has a repeated eigenvalue. So the first thing that we're going to tackle is this idea of a repeated eigenvalue. And remember, that's where the discriminant equals 0, right? That's where that discriminant of the characteristic polynomial equals 0. And 0 eigenvalues are literally what you think they are. They're what happens when an eigenvalue turns out to be 0. What happens when lambda equals 0? What do we do in that case? So we're going to be dealing with the two situations here. And in the first case, we're going to be taking a look at an example where we run into a repeated eigenvalue. So right out of the gate, if we're given a matrix equation like this, we can start off by finding our eigenvalues, which is not tough. We know the process. The process for us is going to involve setting up the determinant of that modified coefficient matrix, which in this case would be -2 minus lambda, and then 1, 0, and -2 minus lambda. Now you might be thinking, hey, look, it looks like they're the exact same thing in both places. Absolutely. And we're going to say, where does that determinant equal 0? What lambda values makes that true? And so right out of the gate, we can come up with our characteristic polynomial, which is going to be this. And what's key about this is these two multiplied together give us a repeated eigenvalue, but only if this multiplication winds up being 0. So with a little bit of mathematical practice, we find out that there really are two possibilities, but they happen to be the exact same value. Lambda equals -2 in both cases. And so what we have is repeated real eigenvalues. Now, if you were to multiply this out, you'd find out that's because your determinant, or the discriminant of your quadratic equation, equals 0. So what do we do with this? Well, in the past, what we would have done is just plowed ahead and said, okay, well, let's try to find out what our eigenvectors are going to look like. But since we only have actually one number to play around with, it seems like there really only be one eigenvector. So let's see what happens. So using the same kind of logic as before, we'd set up our equation and say coefficient matrix times some magical eigenvector x1, y1 must be equal to our eigenvalue, -2, times x1, y1 as well. So this must be true if that really is an eigenvalue. And so after a little bit of manipulation, let me scoot this up so we can see it a little bit better. We wind up with two equations. The first one, top one, is -2x1 plus y1 equals -2x1. And then the bottom is, well, 0x1 minus 2y1 equals -2y1. And you can probably tell pretty quickly that the top equation simplifies into y1 equals 0. But the bottom one does something strange. There's no x involved. And so these two terms, if you move them all to one side, you wind up with nothing equals nothing. And so this top equation tells us something specific. This top equation tells us that we do have an eigenvector that looks like this. Whatever you pick for x, y is always going to be equal to 0. But the bottom equation doesn't tell us anything. The top equation is telling us, oh, the x-axis must be one of your straight line solutions. But this bottom equation literally tells us nothing. And not because it's not true, but because it's always true. In other words, that bottom equation doesn't confirm the top. It just kind of sits there mutely and smiles at us and tells us nothing of any value. So it might be a good idea to take a look and say, hey, what does Maple say about this? So I'm gonna hit pause for a second and pull up Maple and let's see what it says. So taking a look at Maple, I just plugged in, did a quick desolve for our differential equations, our system here, and this is what turns out to give us. So x of t it's got two terms. The first term has got a constant times t, and then the second term is just a constant, and they're both multiplied by e to the minus 2t. The minus 2, we recognize that's our eigenvalue right there, right? But the y of t is only one term. So if we go back and take a look at our original equation here, you'll see that we have a partially decoupled system. So this should look familiar to us because this is dy dt equals negative 2y. So we knew going into it, or we could have known going into it, that we were going to have a partially decoupled situation. So it's almost as if Maple is saying that you have two eigenvalues. You have lambda 1 and lambda 2, and they're the exact same thing, but you have one eigenvector. Let me scoot this up. Oh, sorry, get that stupid camera off the screen here. We found that first one, but what about the other one? What does Maple say about the second eigenvector? Well, again, we can hop back over to Maple and find out. So if you take a look at what Maple says, it seems to be indicating that the second eigenvector is a 0 vector. 0, 0? But 0, 0 can't be an eigenvector because it's kind of the trivial case. It's not going anywhere. It's not doing anything. So there's something weird going on. We know there's a solution. It's a pretty straightforward solution. But using the eigenvector eigenvalues method, it doesn't seem to be working. So back to our screen here, if we tried to make sense of this, what Maple is saying is not making a whole lot of sense. And we know that by desolve, we wound up with a situation that looks like this. X of t was a constant times e to the minus 2t plus another constant times t times e to the minus 2t. And y of t, because we know it's partially decoupled, just turns out to be that c2 times e to the minus 2t. So we wound up with this strange partially decoupled situation, but yet Maple was predicting, or Maple was suggesting, that we had a 0, 0 vector. That can't be true. And the reason it can't be an eigenvector is because it doesn't go anywhere. It doesn't tell us to do anything on the phase plane. So something weird is going on. And in order to make sense of this, we have a formula. Now, normally when I have taught this in the past, what I've done is gone through this example and explained where this theorem comes from. The problem is that it's a little involved. And so what we're going to do is we're going to kind of jump ahead a little bit. We're going to jump ahead to the theorem that's not on the next page, but the following page. So you'll notice, I'm just going to write down here, we're just going to jump ahead to the theorem. And this theorem is, it's kind of a niche thing. It only works when you are talking about repeated eigenvectors, or excuse me, repeated eigenvalues. So I'm going to kind of jump past this next page as blank because normally what I do is leave that entire page open for making kind of the proof of where this thing comes from. Now, if you want to see the proof, I'm more than happy to share it with you. It's also kind of spelled out in the book, in the text, but the proof for this becomes a lot more, well, a lot more than it's worth in the end, especially for kind of a niche theorem. Now, one of the things that you'll notice is that I have a kind of a goofy name for this thing. It's a goofy name because referring to it as the theorem for repeated eigenvalue is just kind of a pain in the butt. I just refer to it as the ballad, as if there's a song about this kind of thing. So I refer to it as the ballad of the repeated eigenvalue. And it basically says, suppose you've got a linear system that has a 2 by 2 coefficient matrix, and you wind up with a repeated eigenvalue. And remember, you could really have a repeated eigenvalue if you're talking about real eigenvalues. Now this makes sense because if you had imaginary eigenvalues, they'd have to be complex conjugates of each other, right? And so the only way you can have a repeated eigenvalue is if they're real eigenvalues. And so you'll notice that means that these two eigenvalues that you have are not actually separated from each other. They're what we call linearly dependent. And so one of them is linearly dependent on the other. That's what we're seeing in the maple output when it says the 0 vector. It's saying the other one is not independent from the first. So the general solution for a system that has repeated eigenvalues looks like this. This is just how it works. And so in the end, the ballad boils down to this formula right here. And this is one of those things where you'll use it a couple of times when you run into repeated eigenvalue situations. Now notice there's only one lambda because there's only one eigenvalue, right? Here and here. But the key for this formula is there's a t value sitting in front of one of those exponentials. So whenever you see a t sitting out front of a solution, it usually means things are not linearly independent. The other thing to keep in mind, or to pay attention to here, is that we have two vectors. One of them looks like a vector with a subscript 0, and the other one has a vector with a subscript 1. Subscript 0 almost always means initial conditions, and so this is the very particular and very special vector right here that basically says whatever your initial conditions are, x sub 0 and y sub 0, those go in here and here for that vector, v1. Could be any initial condition, anywhere on the phase plane. That's where you throw them in. The other vector that gets mentioned is v1. It's this guy right here. And this one is special. This v1 is special. And it's defined as this. Now you'll notice this looks pretty familiar. That is our modified coefficient matrix. That's how we figure out what our eigenvalues are. We find the determinant of that thing. But notice we're going to take that and multiply it by v sub 0. So let's go ahead and do what we did, or do this exact same thing using our previous example. And if you remember, on the previous example, the one that we were just messing around with, we knew that lambda was repeated at -2. And we know nothing about an initial condition. So our initial condition vector, v sub 0, is just whatever initial x and initial y we care to choose. So those two things we have to kind of establish out of the way. The only other thing that I need to know is what is this magical v sub 1, this guy right here. And that's just my modified coefficient matrix with my eigenvalue. So I would take my coefficient matrix, -2, and then subtract my eigenvalue. So minus a -2, and then 1, 0, and then in the diags, -2 minus a -2. And that thing times my initial value vector here. So a little bit of arithmetic is required to kind of spell this out. Sorry, paper's sticking up there. And so when I multiply this out, the first thing that I'm going to recognize is I've got the coefficient becomes -2 plus 2, so that's 0. And -2 plus 2 is 0. So this matrix really simplifies nicely. And so when I multiply it by my column vector here, things get really, really simple. 0 times x1 plus 1 times y1, or times y0, sorry. So this is going to be y0 up top, and then 0 and 0, it's just 0. And so after all is said and done, we have the ability to rewrite, using our formula from up here, rewrite our particular solution for this matrix equation as e to the lambda t, and so that would be e to the -2 t times v sub 0, so whatever my initial conditions are that I want, plus t times e to the lambda t times my v1 that I just found right here. So I'm just color coding so you can see where everything comes from. And that's it. That's the solution. So when you run into a repeated eigenvalue situation, they're actually the simplest of all the possibilities, because all you have to do is find out the eigenvalue, find out that it's repeated, and then use the formula, use the what we call the ballad. Use the ballad, and you're all done. Now you'll notice that this should look an awful lot like the solutions that we had from Maple, right? And see if I can do this without kind of making everything show up weird. So you notice that x of t has two terms, but the y of t, because of the 0 down here, only has the one term, right? And it only has that constant times e to the minus 2t. So that gets us through at least learning the ballad. The next video we'll do an example of how does it work.